a crack thinner than a human hair. 30 meters below sea level, water pressure turns that crack into a cutting torch. The jet can slice through steel, flood a tunnel section in minutes, trap workers in rising water. Engineers know the ocean doesn't negotiate. It tests every weld, every seal, every joint, every single day. One method drills through bedrock beneath the seabed. The other sinks giant prefabricated tubes into underwater trenches. Both fight the same enemy, pressure that never sleeps. But one critical difference determines which method gets chosen, and why that choice means life or death for everyone inside. Underwater tunnels face problems most engineers never touch. The seabed is not one material, it's layers that can shift, settle, and squeeze. Water pressure rises fast with depth, and even a small leak becomes a serious event when the ocean is pushing non-stop. But pressure is only the start. The surface cannot simply pause. Ships still have to move. Ports still have to function. Weather changes the plan in hours. Marine work is expensive the moment equipment is floating. And safety rules in confined spaces slow every task because mistakes don't stay small. Deep underground or beneath the seabed, access is limited. Inspection often means sensors, cameras, robots, or divers, not a quick walk with a flashlight. These constraints kill most ideas early. They leave engineers with two radically different solutions. A tunnel boring machine is a moving factory that eats its way forward. The cutter head grinds rock or soil while the machine holds the face stable. Behind it, everything is choreography. Spoil is carried away, hydraulic rams push the shield, and precast concrete rings lock into place to form the lining. In water-bearing ground, the front of the machine is kept under controlled pressure, often using slurry or compressed air, so the ground doesn't collapse and water doesn't rush in. The advantage is separation from the sea. Waves, currents, and shipping are irrelevant once you're deep enough. The tunnel is continuous, with no huge underwater connections that must be made in open water. Alignment can be tightly controlled over long distances, and the lining is installed as the machine advances. But TBM tunneling is slow and stubborn. Progress is measured steadily, not dramatically. Machines are expensive, and geology can still surprise you. Faults, fractured zones, and water-rich layers can force pauses while the ground is treated or the method is adjusted. You also need big sites at the ends, launch pits, logistics, power, muck handling, and often local production of lining segments. Boring is excellent when conditions match the plan, and painful when they don't. Immersed tube tunnels flip the logic. Instead of creating the tunnel underground, you build it on land as giant sealed sections. You float them out like ships. At the same time, crews dredge a trench across the seabed. Then comes the moment that defines the method. Each section is carefully ballasted, lowered into position, and connected to the one already placed. This is heavy engineering done on a moving surface. The section has to descend under control. It must arrive within a narrow tolerance. Currents push. Visibility can be poor. And during the connection, temporary bulkheads and temporary systems are what stand between the inside space and the ocean outside. The advantage is speed through parallel work. While the trench is prepared, sections can be fabricated at the same time. Placement can move quickly when conditions cooperate. Immersed tube can also work well in soft ground where deep boring might be difficult, or where shallow profiles make a drilled tunnel less practical. But immersed tube construction is at the mercy of the sea. Storms stop operations. Currents complicate alignment. And every connection between sections is a high-stakes event. A bored tunnel has many ring joints, but they're assembled in a controlled environment behind the shield. An immersed tunnel has far fewer main joints, but each one is made in the open world with time pressure and weather risk. Here's what keeps engineers awake: the immersed tube joint. Two massive sections meet underwater and must become one structure that resists pressure for decades. Seals, often rubber gaskets, must compress evenly. Mechanical systems pull the sections together with enormous force. Water must be kept out while the connection is verified, locked, and gradually transitioned from temporary protection to permanent sealing. And the failure modes are unforgiving. If alignment drifts, gaskets don't seat correctly. If ballasting is uneven, a section can tilt and damage the seal. If sediment contaminates the interface, a leak can start immediately or slowly years later as materials age and movement accumulates. So engineers assume imperfection and design around it. They add drainage paths that intercept water before it reaches critical spaces. They monitor pressure, moisture, and movement continuously. They dewater in stages to avoid sudden pressure shocks. They treat the joint like a launch event, planned, rehearsed, checked, and documented, because it's the place where precision fabrication meets a chaotic environment. So which method wins? There's no universal answer. Depth is a big factor. As water gets deeper, trenching and placing immersed sections becomes harder and riskier. At some point, it can be safer to go deeper into the ground and bore below the seabed. Geology matters just as much. Hard rock can favor TBMs built for it. Very soft soils can favor immersed-tube, where the tunnel can be bedded and protected rather than forced through unstable ground. Mixed ground is dangerous for both. It can complicate boring, and it can complicate trench stability and settlement. Then come the practical constraints. Do the shores have space for huge portal sites and continuous logistics? If not, floating sections from a remote fabrication site can help. Is the crossing in a narrow, heavily trafficked channel? If so, minimizing surface disruption can push the choice toward a bored tunnel. Is the schedule brutal? Immersed-tube can compress time if weather and permits cooperate. Is dredging limited by environmental windows? Then a slower method might still be more predictable. The method is chosen where engineering reality, risk tolerance, and logistics overlap. Where the tunnel meets land, different physics takes over. Approaches load the ground. Soft soils compress. Uneven settlement can bend structures and strain joints. Settlement isn't always a surprise. It's often expected, but it must be managed. That's why projects use ground improvement, pre-loading, or deep foundations depending on conditions. And that's why instrumentation is not optional. Settlement gauges, inclinometers, and structural sensors track movement in real time. If behavior diverges from the model, work slows down or stops because the land interface can damage a perfectly built underwater section. Portals are also the flood weak point. A tunnel below sea level is a path for water if the ends are exposed. Even if the underwater structure is sound, storm surge and heavy waves can threaten the entrances. That's why flood protection at portals matters. Seawalls, barriers, and drainage designed for rare extremes, not daily weather. The gate is not just a door. It must seal under pressure. It must still allow everyday traffic. It must be reliable during the exact conditions when everything else is stressed. Because many tunnels don't fail in the middle. They fail at the edges, where sea meets land and weather meets infrastructure. An underwater tunnel is never done. It's monitored like a living system. Sensors watch joints. Strain and movement are tracked to catch slow deformation early. Water detection runs along low points. Pumps handle expected seepage, because real structures are designed to manage water, not pretend it will never appear. Ventilation keeps air safe and also reduces humidity that accelerates corrosion. Maintenance is scheduled, systematic, and relentless. Teams inspect joints, walls, and drainage. Sumps are cleaned before they clog. Backup pumps are tested, not trusted. Access routes and service spaces exist because engineers assume repairs will be required. The goal isn't perfection. The goal is controlled degradation, detected early, contained fast, and fixed safely. Now the real test. not a lab test. The worst day test. A storm surge raises sea level higher than normal. Waves add dynamic loading. Heavy rain overwhelms surface drainage. At the same time, one joint, quietly aging for years, finally starts to leak more than the pumps were handling yesterday. Sensors see the change first: pressure, flow, moisture, where there should be none. Alarms trigger. Operators isolate the affected zone. Barriers close to protect the rest of the tunnel. Pumps ramp up. Drainage paths do what they were built to do: buy time. The objective is not heroics, it's control. Keep water in one compartment. Keep evacuation routes clear. Prevent secondary failures. Inspection starts under pressure. If divers can't go, robots go. If the leak can't be sealed immediately, the system shifts into containment mode and keeps shifting until the situation is stable. Traffic is rerouted. Entry is restricted. Nobody rushes toward the problem, because underwater tunnels punish impatience. This isn't a story about one incident. It's the philosophy behind the design. Engineers assume leaks will happen. They assume storms will hit at the wrong time. They assume equipment will fail during a maintenance window. So redundancy is built in. Backup pumps, independent power, compartmentalization, multiple sealing layers, and monitoring that catches small problems before they become fast ones. Construction builds the tunnel. Engineering builds the system that survives when conditions exceed the plan, and the ocean tries again. If you want more engineering that works hardest when everything else fails, subscribe.